it can be added to number. And whenever it's out, so whatever is out of the function notation, this is for the vertical translation. And whatever is written inside the function notation, this is for horizontal translation. But you must take care that we change the sign of what's inside. So for example, if you have x plus 2, we just change the sign and put it here. And if we have vertical, we don't change, we just keep it as it is. So if you notice, minus a here has been written as a, and the b has been written as it is. So we change the sign of the number inside the function notation or inside the brackets, and whatever is out, we just keep it as it is. This is regarding the translation, and we're going to take examples to clarify more. Regarding, we have two types of stretching the graph vertically and stretching the graph horizontally. So whenever here is a number is multiplied by the function notation, this means we have vertical stretch, or the function has been stretched vertically. What do we do in the case of stretching vertically? We just multiply the y-coordinates of the original function by the number which is given here. So we multiply the y-coordinates of the original function, all the y-coordinates of the original function will be multiplied by the number which is written here, and we're going to take an example. What about the horizontal stretch, or stretch in the x direction or x-axis? Here is horizontal stretching. Horizontal stretch, it will be, the number will be written here inside the function notation or inside the function itself before the x. So what do we do here? We divide all the x coordinates by the numbers. So whenever we have the x coordinates of the original function, what do we do to do the horizontal stretch? We divide all the x coordinates by the number which is here. And this number can be integer or it can be fraction. We're going to see all the cases here. The reflection, we have two types of reflection. Reflection in the x-axis, if the function looks up like this, for example, it will be reflected down, or if it's down, it will look up after changing this. And in the y-axis, for example, if the function is on the right, it could be on the left. If it's it's on the left, it will be on the right. So what do we do exactly here? Here we just multiply the sign, the y coordinates by -1, or we can change the signs only of the y coordinates. Here you can change or multiply by -1 the y coordinates. Here the x coordinates will be multiplied by -1. Here x coordinates. So briefly again, the translation of the function will be in this form. If there is something added or subtracted to the x inside the function notation, it means it has been translated horizontally. So we just change the sign of what's inside here. And what's outside, this is vertical translation, but you will not change it, you'll just keep it as it is. So here, this is A and B. Regarding the stretch, we have two types, a stretch vertically and a stretch horizontally. Regarding the vertically, you will multiply each y coordinate by the number which is here, if it's integer or if it's a fraction. The same thing will be happening with the x coordinates, but by division, if the number is written inside the bracket, what you will do is you will divide each x coordinate by the number in here, if it's integer or if it's a fraction. Regarding the reflection, we multiply, if the negative sign is out of the function notation, you multiply all the y coordinates by -1, and here if the negative sign is inside the function notation or inside the brackets, we multiply all the x coordinates by -1. So let's see briefly the graph, how they look like after transformation. Here the translation, here is if we have, for example, a number is written out of the function notation, this means vertical translation in the vector of 0 and 1, y0, because there is nothing here in the brackets of the x, so we have no horizontal translation. We have only vertical translation, 1 unit up. So if here is the function, the original function, which is the black one, it has been shifted or translated 1 unit up according to the first sentence. And here, if we have a function of x plus 2, what did happen here? We translated the old function by a new one. Here, this by -2, we said we changed the sign of what's inside the bracket, so it would be -2 and 0. The translation by this vector, -2 and 0, because we changed the sign here to be horizontally -2. So if the 0 here is one of the points on the original, so we'll shift it 2 steps to the left. So instead of 0 and 0, it's now -2 and 0. We have no vertical translation here because nothing is added or subtracted to the function notation. This is briefly how to translate the graphs, and we will take past paper questions to check your understanding. The vertical stretch and horizontal stretch in here, we have two cases. In case of the number which is written before the function notation is integer or it's a fraction, we say it in common. What do we do whenever the original function is here and down no function here is number is multiplied by the function notation, if it's integer or fraction, it means we have vertical stretch. So as you see here, the function will be stretched vertically. In case of the number is integer, so the function becomes a bit tighter, like you see the red one here. You multiply each y coordinate by 2, and here you multiply each y coordinate by half, and then you represent. If someone asks from where you can get the coordinates or the points, whenever you have the first or the main function is given in the question, you can get out some points from the graph itself. You can list them here and start applying or implementing these transformations in them. And we're going to see a question like this. Regarding the horizontal stretch, we said the number would be multiplied by the x inside the brackets, like here 2 and here 1/3. This is horizontal stretch. What do? We divide by all x coordinates would be divided by 2 in this case, and here all x coordinates would be divided by third. So if the original one is the black graph, if you do horizontal stretch in case of 2x, because this is integer, it will be look like this. It becomes more tighter in here, but if it's a fraction, it will be more wider in this case. So here we divide all x coordinates by 2, and here we divide all x coordinates by 1/3. And as I said, we're going to see more examples on this, including in the past paper. The last type of transformations is reflecting the graphs or the reflection of the graphs. As we said, whenever the function it has negative sign written before the function notation itself, it means this would be reflected in the x-axis. Like for example, here you have the original one is the blue, and here it has been reflected in the y-axis. It becomes the green. Instead of it was looking upwards. Now the green is looking downwards because it has been reflected. If you have the blue one, here is the original, and then you have the negative signs inside the brackets. So if it's here on the left side, it has been shifted on the right side. But you don't know how it will be reflected by how many steps. You can do what? You can multiply in this case. If the negative sign is out, you multiply all the y coordinates by -1. But if the negative is inside the function notation, you will multiply each x coordinate by -1. So in this case, the x coordinates will be multiplied by -1, and here the y coordinates multiplied by -1. Okay, so let's move to an example to clarify these points. By the way, maybe there will be a question, combined transformation, which means there will be stretching, reflection, and translation all at the same time. So this can be included in there. As you see here, we have a question from the past paper, how to do this one regarding the transformations. And we said transformations can be implemented even in the trigonometric graphs. Here, as you see in the given question, it says y equals sine theta. So we have a trigonometric function as it's written here, between the range 0 to 360. We need to find y equals 4 sine theta. So In this case, we need to know the transformation that happened. Since you have 4, the main function is y equals sine theta. So this can be considered as the function notation. Here we have y equals 4 multiplied by sine theta. So this is vertical stretch has happened to the function. The question says state the coordinates of the minimum point on the curve of the equation y equals 4 sine theta. So the new graph y equals 4 sine theta has been stretched vertically. We need the minimum point only. As you see here, we have one maximum point and we have one minimum point. So the old point for the main graph, or the original graph, is 270 and -1 for the original. But now we have this one has been stretched vertically. So as we know, stretching vertically, we multiply all y coordinates by 4. Okay, so I'm going to take the minimum point, multiply only the y coordinate by 4. So it will be 270. And then we have -1 multiplied by 4, it will be -4. So the minimum point in here for this new graph will be 270 and -4. Then the rest of the question says we need to find here on diagram 1, we need to draw sketch y equals 1 plus sine theta, and we need to draw y equals tan theta. Here a transformation has happened to this one in BI, y equals 1 plus sine theta. The original function is y equals sine theta, and there is numbers added, and it's out of the function notation. It's not added in the bracket. So it means this one has been translated by 1 unit up. So it means we will shift this one by 1 unit up. So we have another graph, can be done down there. So now we're going to draw 1 plus sine theta, we said. It will be shifted 1 unit up. Here is the sine theta, the original one. So just your move, shift this one unit up, shift this point 1 unit up, shift this point 1 unit up here, and this will be shifted here, and this will be shifted here. So it will be drawn like this. So it is the 1 plus sine theta has been drawn, and it was required to draw the other one is y equals tan theta, and then we need to find the intersection points between them. So we just draw here tan theta, as you know, it will be having separate lines here. This is the dashed line. It will be drawn like this. Here. So we need to find the intersection points for this one, but this is not our topic. We're talking about the transformations. We're going to move to another one for the transformation. And this question says a curve has equation y equals f of x, where f of x is x minus 4 multiplied by 2x plus 1 whole squared. We have the curve touches the x-axis at the point P and crosses the x-axis at the point Q. So whenever it touches or crosses the x-axis, it means y equal to 0. So the f of x equal to 0 here. So when the y is 0, we have x minus 4 is equal to 0, or we have 2x plus 1 equal to 0. So the x equals -half. And here x equals 4. So the point P as a first point would be -half and 0. Disregarding point A. In point D, we're going to skip B and C because they are not included in the transformation topic. We're going to do point D. It says the curve of the equation y equals f of x plus a, which is inside the function notation. It means horizontal translation. Here, where a is a constant, passes through the origin O, state the possible values of a. So now, after the transformation that happened from this function to this function, the curve will pass through the point 0 and 0. As we know that it was passing by the point 4 and 0 on the x-axis and negative half and 0 on the x-axis as well. So now we need to know after the transformation horizontally, we need to know when it's going to be 0 and 0 here. It will be shifted. So from negative half, we're going to shift it on the right direction to become 0 and 0 instead of negative half and 0. So negative half, we will move half to the right. So half to the right, if we want to put it inside the function addition, we will change the sign. So it will be x minus half. This in case it would be half. And here, in case if we have 4 and 0, it will go to become 0 and 0. We will move 4 steps to the left, which means negative 4. So we'll move from 0, 0 to 4, 0, or 4, 0 to 0, 0. We'll move 4 steps to the left. So to become inside the bracket, what we will do is, it will be 4, and here f of x plus 4, because we changed the sign. So a maybe can take the value of negative half or positive 4, because we shifted horizontally. Why horizontally? Because the a is included inside the bracket. Let's see another question. How to do transformation from the past paper questions. We can move to another point in here for the past paper questions. Here the graph says, the question says, figure 2 shows the plot of part of the curve y with the equation y equals cosine 2 sec 2x with x being measured in radians. The point P shown on figure 2 is a minimum point on the curved state the coordinates of. So as you see here, we have the horizontal stretching that happens because the 2 is multiplied by x in the function notation. So when the angle is multiplied by number, this means horizontal stretch, but when the function itself or the trigonometric identity itself is multiplied by a number, for example, like 2 cosine x, this means vertical stretch, but here means horizontal stretch. So what should we do is, as we know that when I said to you before, you will divide here all the x coordinates by 2. But let's try to compare between the cosine x and the cosine 2x. The cosine x, the original that was, if we have the angle 0, then we have the angle pi over 2, because the radian measure, we have pi, we have 3 pi over 2, we have 2 pi. The original, the 5 main points, which is 0, 90, 180, 270, 360. Here the 0 was having 1 as a y coordinate, and here 0, and here we're having the negative 1, and over here we're having 0, and then we have 1 in here. So in the original, the minimum point was in here, pi and negative 1. This was the minimum point in the original. But here we don't have the original, we have cosine 2x. The one after transformation is 2x. So what we will do to the x is we will divide the x coordinate by 2 in here. So this point will be changed into pi over 2 and negative 1 in this case. We can see here in this question, question 7, in a past paper, it says figure 3 shows part of the curve C1 of the equation y equals 3 sine theta where x is measured in degrees. So as you see here, it's mentioned y equals 3 sine theta. So 3 is multiplied by the trigonometric identity by the function. So it means we have vertical stretch, which means you will divide all the y coordinates. You will multiply all the y coordinates by 3. The point P and the point Q lie on C1 and are shown in figure 3. We need to find coordinates of P and the coordinates of Q. So as you see here, this is the maximum point in this graph. This is the maximum of the new one, and here we have this is the ending in here. where it stops on 0. So we can compare it with the original sine x in degrees. We have the mean 5 angles, 0, and we have angle 90. Then we have 180, 270, and 360 degrees. So where the sine of 0 is 0, sine of 90 is 1, and then we have the sine of 180 is 0, sine of 270 is negative 1, and we have the sine of 360 is 0. So this for the sine theta before any transformation happens. Now the maximum point for the sine theta is 90 and 1. This is the maximum point before any change happens. This was the maximum point. But now we have 3 sine x. It means the 3 will be multiplied by the y coordinates, so the p can be 90, and here 1 by 3 is 3. So we have the coordinates of the point p in here. We get point q in here. Here, this was the 90 degrees, and then here is the 180 degrees. Then we have the 270 degrees in here. Then 360 degrees. Then if we add 90 more, it will be here 150 degrees. Then we will have here at 90, it will be 540 degrees. And as you see, the y coordinate for this one is 0, so this will be 540 degrees and 0, because 0 as a y coordinate multiplied by 3, it will give you 0. Regarding part B, it says a different curve C2 has equation equals y, has equation y equals 3 sine theta, sine x plus k, where k is a constant. The curve C2 has a maximum y value equals 10, so y equals 10 as the highest value. Point y is the minimum point of C2 with the smallest positive x coordinate. State the coordinates of R, and we need to find R in here. So we can first of all talk about the maximum point. The maximum is happening at the 90, as we know, when we have the sine x as the smallest x coordinate. The maximum is happening in the 90 as the smallest x coordinate. So let's try it in here. It will be y equals 3 times sine 90 added to k. And regarding the maximum, the y value will be 10. So 10 here equals 3 sine 90. We just need to know what's the value of k here plus k. As we know, sine 90 is 1, so 3 by 1 is 3, and the k will be 7. So the function has been shifted vertically or upwards by 7, translated by 7 units up. So the k is 7. Now we need to know the point R, the minimum point C2 with the smallest positive x coordinate. Minimum point when the x is the least in the positive side. So here the maximum with the smallest x coordinate is 90, and the minimum with the smallest x coordinate is 270. So now we have known that the x is 270, so the point R is having coordinates 270 degrees, and we need to know the y coordinate. So if we apply here, or just replace the value of x in here, y equals, we have 3 sine 270, then we add 7, which is the k value. Here we know that sine 270 is negative 1 because it's a minimum. 3 times negative 1 is negative 3 plus 7 is 4. So the y coordinate on the minimum point here, it will be 4 for this one. So the answer, the coordinates of R is 270 degrees and 4.